Hello friends, in this course so far we have learned how to find radiative heat exchange between diffuse surfaces. In this lecture we will learn radiative heat exchange between specular and partially specular surfaces. So, diffuse reflection, basically we have what we introduced in this previous lectures, a quantity called radiosity. So, the good thing about diffuse surfaces is that we do not have to distinguish between emission and reflection. So, let us say we have a surface and this is a diffuse emitter, that means it emits radiation uniformly in all direction, and the same surface receives some radiation, it may be coming from a single direction or it may be diffuse also, but the reflected radiation is diffuse. Okay. So, we have diffuse emitter and diffuse reflection, and the combined can be diffuse also. Okay. So, this is also combined. So, we do not have to distinguish what is emitted and what is reflected, we call it radiosity. Okay. So, that was a powerful approach of dealing with the diffuse surfaces, but when a surface is partially specular, the method for analysis becomes quite different. Okay. What we mean by partially specular surfaces is, we have a surface and the radiation incidence on this circle leads to some radiation reflected like a diffuse reflection, and some goes in a particular direction. Okay. So, there are two components of this radiation, reflected radiation, one is diffuse and one is reflected. For example, mirrors, now mirrors are finding applications in many problems, especially in solar energy. So, these mirrors and many other surfaces, they behave like specular surfaces or partially specular surfaces. So, as such the method of analysis is complicated unless and until we do some simplification. So, the simplification here is that the diffuse the surface may be having a component for specular reflection, but it emits radiation and it absorbs radiation diffusely. So, epsilon and alpha do not depend on angle. So, epsilon is equal to alpha is equal to epsilon prime is equal to alpha prime. So, emission and absorptance, emittance and absorptance do not depend on direction, they are diffuse, and by this logic the total reflectance rho is also going to be diffuse. Okay. Now, we divide the total reflectance into two components, the diffuse component and the specular component. Okay. Now, one may ask, so how the directional effect of specular reflection is coming into play. So, so the directional effect of specular reflection is coming into play just by its dependence on rho s, which is not continuous, which is in a given direction. This point will be clear in the next slide. So, let us say we have a surface as is shown on the left hand side. This surface is a partially specular surface. The reflectance is strongly dependent on direction, as is seen, it strongly reflects at an angle of theta is equal to 0 degree and at an angle of theta is equal to 15 degree and so on, but it also reflects at other angles between 0 and 15 degree, but the reflectance decreases gradually. So, this is the real behavior of a surface, a partially specular surface. Now, as such it is very difficult to solve of a problem if the properties, the reflectance properties are behaving in such a way. So, we have to approximate it, and the way we approximate it is we write the total reflectance rho as a sum of diffuse and specular component. So, the term, so this is the diffuse part, that is uniform in all directions, and then there is a specular component which is a finite value in a given direction. Okay. So, there is no continuous variation of this in versus theta, only we have a specular reflection in theta is equal to 0 degree, 15 degree, 30 degree, 45 degree and so on. But between 0 and 15 degree there is no reflection, no specular reflection. There is a diffuse reflection between 0 and 15 degree, but there is no specular reflection. So, this simplification we have to do if we want to solve this problem analytically. Okay. Just like we have defined diffuse view factor, we can also define a specular view factor. So, specular view factor is defined as the total amount of diffuse energy leaving an element dAi and received by another element dAj directly as well as after any number of specular reflection. So, please note we are only interested in specular reflection while defining the specular view factor. The diffuse reflection is not accounted here in the diffuse view in specular view factor, and in the denominator we have total diffuse energy leaving dAi. So, as is clear in this image, let us say we have a surface dAi, okay. Energy is leaving diffusely in entire solid angle 2 pi. Some of this energy directly travels towards dAj, some energy travels towards A and specularly reflected towards dAj, some energy first travels towards B, undergoes specular reflection at B, received by surface C, undergoes reflection, specular reflection from C, and then arrives at J, dAj. So, there are direct reflection, multiple reflection that are accounted in the definition of specular view factor. So, we can write down a small element specular view factor dF superscript s for specular, dAi to dAj as equal to the direct view factor dF dAi dAj. This is the direct and diffuse view factor. So, this is diffuse and direct, okay, between dAi and dAj. We also have contribution from reflection. So, we write the specular reflectance rho as for the radiation coming from A after reflection from A, and then view factor from dF small view factor dAi A dAj. I will explain the term dF dAi A dAj, and then double reflection from B and C, and similarly the view factor. Okay. All these view factors are diffuse view factors and we have not used any superscript s, while the view factor on the left hand side is specular view factor and we have used the superscript s. We may have other possible reflection paths also, but in this particular picture we have only 3 paths: direct, single reflection from A and double reflection from B and C respectively. So, the quantity dF dAi A dAj is defined as diffuse view factor between image of dAi, now which image reflected from surface A and dAj. So, we are talking about the view factor between the two surfaces, where one surface is real surface dAj, while the other surface is basically an image of dAi. So, dAi A is basically an image. Okay. It will be clear in the next image next figure. So, here this is the surface element dAi, it is reflected from B. So, this is the mirror surface, its image in mirror B is formed here. So, when we talk about the view factor between an image and surface, we have to take into account this area. Okay. After the second reflection in mirror C, the image appears here. So, this is the image of the area DAI after twice reflection from mirror B and mirror C. So, the definition of view factor DF between DAI BC to DAJ means we are talking about the area DAI after reflection from B and C, and this is the image. So, this view factor we are interested in between this and between this area. Okay. So, our specular view factor can be written as multiplied by DAI and applying the reciprocity theorem, DAJ, DF, DAJ, this is direct, this is between AJ and the first image between AI and mirror A, and double reflection, again we have applied the reciprocity theorem. Now, one thing you should keep in mind is, as from just purely the geometric point of view, we can define DAJ DAI A, that means the view factor between an element AJ and an image of AI. This is again the same area as of that AI is basically equal to DAJ, the image of AJ to DAI. That means we can take image of any of the surfaces and the view factor will not change. Okay. Either we take image of AI in mirror A or we take image of AJ in mirror A, it is the same. Okay. So, that relation we have invoked here. So, we have converted DAJ to DAI A into DAJ A DAI, and same thing here. Okay. So, this relates to DAJ, the entire these three terms basically are equal to DAJ DFS, the specular view factor from AJ to DAI, and looking at these two terms, what basically it appears is the reciprocity theorem. So, reciprocity theorem is also valid on specular view factors. We have proved it earlier that it is valid for diffuse view factors, and in this slide we have also proved that reciprocity theorem also holds on specular view factors. Okay. Now, the summation relation for diffuse surfaces was summation Fij is equal to 1, that was the summation rule for diffuse view factor. For specular view factor, it can be proved that the relation 1 minus reflectance, specular reflectance rho j s Fij s summed over surfaces 1 to n is going to be equal to 1. So, the summation rule is different for specular surfaces and diffuse surfaces. So, let us do one problem and find out the specular view factor for this geometry. We have two parallel plates, infinite parallel plates. The first surface has reflectance rho 1 s, the specular reflectance, and the second surface has reflectance rho 2 s. Okay. So, any radiation leaving surface A1, the small element dA1 will directly travel towards A2, it will undergoes reflection with reflectance rho 2 s, it may undergo reflection again with magnitude rho 1 s, rho 2 s, and so on. So, there may be multiple reflection between these two plates. So, we have to find out the combined specular view factor between these two plates. So, let us do the solution for this problem. So, we have a one dimensional problem here. Okay. So, the dimension of the plate in x direction x tends to infinity. It is a one dimensional problem. Okay. So, we from this we can basically write that f d1 to 2 specular is basically equal to f1 to 2 specular. Now, why? Because f1 to 2 specular is basically integrated over f d1 to 2 over dA1, and because of the one dimensionality of the problem, this does not depend on the location. So, we can take it out f d1 to 2 at any location. Okay. So, f d1 to 2 specular is same as f1 to 2 specular for this particular configuration. So, now let us write down the view factor. We have already defined this relation. So, view factor between f d1 to 2 is made up of number of components. The first component is direct, this is going to be 1. Okay. As you can see from this geometry, all the radiation leaving this surface will actually reach the top plate. This is A1, this is A2. There is no other way it can escape. So, all the direct radiation will reach surface A2. So, this is going to be 1. Then the second part is the reflected component. So, we have the reflected part, this is going to be rho 2 specular, okay, and this is going to be rho 1 specular times rho 2 specular. Just look at the relation once again. So, we have rho A specular times the view factor between the image dAi and dAj. Okay. So, that same thing we have done. So, we have taken the reflection from the surface 2, okay, and this will be plus similarly rho 1 rho 2 specular square and so on. So, this is how we are basically defining this view factor, and we can, this is a geometric series, we can write down this as 1 minus rho 1 specular rho 2 specular. Okay. So, this is going to be our view factor. Okay. So, f d1 to 2 specular is simply equal to this value, and this is equal to f1 to 2 specular. Okay. And also because of symmetry, f1 to 2 specular is equal to f2 to 1 specular. Okay. So, all these view factors are basically the same. Okay. So, so again just look at this one, energy directly leaving has a magnitude equal to 1, energy leaving after 2 reflection is rho 1 rho 2 times the original intensity, and similarly this is going to be rho 1 rho 2 square and so on. Okay. So, there will be multiple reflections. So, after multiple reflections this is going to be the view factor. Okay. Now, one thing that you should observe here is, for a special case, let us say rho 1 s is equal to rho 2 s is equal to let us say 0.5. Okay. Now, for this the view factor f1 to 2 specular will be equal to 1 over 1 minus 0.5 into 0.5 is equal to 1 upon 0.75. So, this 1 to 2 specular view factor can be greater than 1. Okay. So, as compared to diffuse view factor, the diffuse view factor will always be less than 1 and greater than 0. The specular view factor f1 to 2 can be greater than 1, and that is why the relation for summation for specular view factor is given by summation j is equal to 1 to n 1 minus rho j specular Fij specular is equal to 1. And the basic logic why this is coming greater than 1 is because radiation leaving a particular surface is undergoing multiple reflection, and all those contributions are being added up before they finally reaches the other surface. So, that is why the specular view factor can be greater than 1. Now, based on this information and this knowledge of view factors for specularly reflecting surfaces, we will solve for heat transfer between these surfaces. The theory is pretty much similar to what we have done for diffuse surfaces. We have a surface, this surface is partially specular, it emits radiation diffusely, that is why epsilon times the black body emissive power. It emits, it reflects radiation diffusely. So, there is a reflected component, a diffuse reflected component, together with the, we call this radiosity, just like we defined radiosity for a diffuse surface. The other term, that additional term, that is only for this partially specular surface, is the the specular reflected component rho superscript s times h, where h is radiation. So, this is the additional component. So, we write an energy balance for this equation. Heat flux is equal to energy emitted minus energy absorbed, energy emitted, diffuse energy reflected, sorry, this is diffuse reflection, this is specular reflection. So, this is the total amount of energy leaving and this is the energy amount received. Okay. We can define surface radiosity as we have done it for the diffuse surfaces, just by including the emission and diffuse reflection. So, in the definition of radiosity, we do not include specular reflection. Substituting this value of J into this equation, we get heat flux is equal to diffuse radiosity, that is energy leaving diffusely, minus the 1 minus specular reflection times HR. Okay. So, this is the absorption term. Okay. So, we can eliminate HR, the irradiance, and we can solve for the heat flux just like we did it earlier. So, substituting the value of or eliminating the radiosity between these equations, we can write down the heat flux Q as epsilon upon the diffuse reflectance rho d, 1 minus the specular reflectance times EB minus JR. Okay. So, here we have unknowns in the form of flux and radiosity. Okay. So, we have to eliminate radiosity also. Okay. Now, we need to find out irradiation before we solve for radiosity. The expression, the mathematics involved is pretty similar to what we have already done. The radiosity is basically made up of emission and diffuse reflection. So, rho d is the reflectance and this is total amount of irradiation H. Okay. In the bracket we have total amount of irradiation, this undergoes diffuse reflection. So, radiosity is made up of these two components. So, we can calculate the radiosity using the relations that we have already developed for gray diffuse surfaces. So, there is no difference here, this entire thing is same as done for diffuse gray surfaces. Okay. The only thing that has changed is basically the specular reflectance that appears basically in this relation, in the relation for heat flux. The expression of J does not change. Okay. So, again as we did in the previous cases of diffuse black and gray enclosures, we divide the enclosure into number of finite length or finite area flat surfaces. Okay. So, the integral can be now converted into a summation. So, J is equal to 1 to n. So, n surfaces, we have divided the enclosure into n surfaces. Okay. So, integral then converted into simply summation, radiosity times the specular view factor. Okay. And when, as from previous argument, the radiosity may be uniform over the surface, but heat flux is not, because the view factor changes over the surface. So, radiosity may be same, it may not be a function of r over the surface, but heat flux is a function of r because the view factor is a function of r. So, we have to take an average. Okay. So, we have to define an q average by taking an average over each flat surface, and when we do that we define radiosity for a surface j I as averaged emission from the surface, average irradiation on the surface multiplied by diffuse reflectance. So, this is average values. Okay. This is local values of radiosity, but on a given surface. Now, with just a few manipulation, the final equation for radiative transfer. So, this is the final equation for radiative transfer between gray specular partially specular surfaces. Okay. So, this is the expression for partially specular surfaces. This energy balance we will apply to solve a problem. Now, this problem we have solved in the case of gray surfaces also. When we solve this problem, the vertical plate that was used as a reflector to increase the efficiency of this collector plate was not a mirror, it was basically a diffusely reflecting surface. So, in this example that we have solved earlier also, we have a collector plate that receives solar radiation. We have already noted earlier that the absorptance or the amount of energy received by this collector is very poor if there is no reflector plate put adjacent to it. In the example that we did earlier, the reflector plate was made up of gray surface and it increased the efficiency of the collector significantly. Now, in this particular example, the same configuration, but the reflector plate, the vertical reflector plate instead of gray is basically specular, purely specular, and has a reflectance, a specular reflectance of 0.9 or the emittance of 0.1, and we will see that when we put mirror a specular surface instead of a gray surface, the efficiency of the collector is going to significantly improve. So, let us solve this problem. So, we will first write down the energy equation for the surfaces, and then we will use this equation. So, this equation we will use and we will write this for the two surfaces. So, surface 1 so we write this as 1 minus rho 1 s specular, F11 specular, EB1 F12 specular, EB2, this is the left hand side, is equal to 1 upon epsilon 1. The collector plate is gray, Q1 minus so this is the energy balance equation for the surface 1, and same thing we do for surface 2. So, minus 1 minus rho 1 s F21 s EB1 plus 1 minus rho 2 specular F22 specular EB2 is equal to minus rho 1 diffuse upon epsilon 1 F21 specular Q1 plus 1 upon epsilon 2 minus rho 2 diffuse upon epsilon 2 F22 specular Q2 and plus H naught 2 specular. So, we have just written the energy equation, energy balance equation for the two surfaces. Okay. Now, first thing that we will do is looking at the view factors. Now, this particular configuration is very specially chosen because although we have a specularly reflecting surface, but the specular view factors all turn out to be 0. So, the first thing that we will look at is F11 specular, that is any radiation leaving surface 1, any diffuse radiation leaving surface 1, that is the collector plate, after specular reflection or directly, is it coming back to 1. So, let us look at the configuration. The radiation leaving diffusely from this surface, it travels towards mirror, but after mirror it will just escape, it will not come back. Okay. And directly there is no way it can come back. Okay. So, this will be equal to 0. Now, F22, any radiation leaving surface 2 diffusely and after specular reflection, but surface 1 is not specular, it is diffuse. So, this is also 0 because surface 1 is not specular. Okay. Now, F122 is specular. So, what is this? F122, any radiation leaving the collector plate diffusely and arriving at 2, okay, after directly or reflection. So, it will have direct component plus reflection, specular reflection component, as we have already done it, but since there is only one specular surface, this is going to be 0. So, F12 is basically equal to direct component. So, F12S is equal to F1 diffuse. Okay. And similarly, F21 specular is equal to F21 diffuse. Okay. So, diffuse view factors we can calculate from the table, we already know that. Okay. The value of the view factor basically for this configuration is equal to, so let me give you the value, F12 is equal to 1 by 4 and F21 is equal to 1 by 3. Okay. So, we have calculated the view factors now in this equation, and let us now solve this problem further. So, we have now energy, with this simplification also the reflector plate is insulated. So, Q is equal to 0. So, with this simplification the energy equation reduces to EB1 minus epsilon 2 F12 EB2 is equal to Q1 upon epsilon 1 plus H naught 1 specular and minus F21 EB1 plus EB2 is equal to minus 1 upon epsilon 1 minus 1 F21 Q1 plus H naught 2 S. So, there is almost the effect of specular reflection we have kind of all eliminated. Okay. Most of the terms in this in these two equations do not depend on anything specular except H naught 1 and H naught 2. Okay. So, what is H naught S and H naught 1 S and H naught 2 S? So, H naught 1 S is irradiation on surface 1 from outside, okay, directly or after specular reflection, and this is basically what makes the difference. Okay, because surface 1 the collector will receive radiation directly as well as after reflection from the mirror. Okay. H naught 2 S is similarly irradiation on surface 2 directly or after reflection, specular reflection. Okay. Now, surface 1 is not reflection, so this term will be 0. Okay. So, H naught 2 S is basically the directly received radiation only. So, H naught 2 S is basically H naught 2, that is it. Okay. There is no reflected part into this. So, let us write down this value of H naught 1 s and H naught 2 s, and then the problem will be pretty easy to understand. So, H naught 2 s is simply equal to Q sun, which is given as 1000 watt per meter square, and sin psi, where psi is given as in this angle, the psi, this is the angle, and this value is given as 30 degree. Okay. Now, one more thing that is needed in the evaluation of H naught 1 s, H naught 1 s includes the direct radiation from the sun plus anything that is reflected from the mirror. Now, mirror, after reflection, the mirror will not reflect the radiation on the entire collector plate, only this part of the collector plate will receive radiation after reflection. As you can see from this image, radiation hitting here will hit here, and radiation leaving here, hitting here on the mirror will reach here. Okay. So, this part of the plate will not receive any radiation after reflection, only the first or the length L2 tan psi will receive radiation, the reflected radiation. So, we have to take an average over this value. Okay. So, we define H naught 1 s as direct component. This is the direct irradiation of collector plate from the sun, and then the reflected part rho 2 s Q sun cos psi. Okay. This is the reflected part, but we have to take an average because the plate is receiving radiation only at fraction of its length. So, we have to define an average. So, we define L2 tan psi by L1, where L2 is given as 60 centimeter. So, L2 is given as 60 centimeter and L1 is given as 80 centimeter. So, we have to take an average of these values. Okay. So, now we have all the information. So, we put the value of H naught 2 s and H naught 1 s in these equation. EB1 Q2 is 0, the temperature of the surface, the collector plate we know. So, everything is known, and when we solve it, we get a value of Q1 as equal to minus 298 watt per meter square. Minus sign denotes that the energy is basically incoming energy into the collector. If it is plus, that the energy is leaving the collector. So, total minus 298 watt per meter square out of 1000 is basically received by the collector. Okay. If we do not use mirror, then energy simply Q1 no mirror will be equal to EB1 minus Q sun cos psi by 1 upon epsilon 1 is equal to minus 12 watt per meter square. This is nothing. Okay. Only very less amount of energy is received if we do not use mirror. Okay. And that much amount of energy may be actually lost due to convection and other losses. So, we can understand the importance of mirror in this problem. We solved this problem with the gray reflector also in the one of the previous classes, and the result we got was minus 172. Okay. So, I will write down this result here. With diffuse gray reflector, we got Q1 as minus 172 watt per meter square. Okay. So, compared to minus 172, we are receiving minus 298. So, that basically explains how important the mirror is in this example. If you use a diffuse reflector and if you use a specular reflector, it makes hell lot of difference. So, specular reflector is going to increase the collector efficiency significantly. The collected radiation from minus 172 watt per meter square has increased to minus 298 watt per meter square, and this is significant improvement. So, I end this lecture here. In the next lecture, we will discuss combined mode of heat transfer, where we have thermal radiation together with other modes of heat transfer like conduction and convection, and we will understand how the combined radiative heat transfer with conduction and convection affects the performance of a equipment. Thank you very much.